Next we will see the operating characteristics of compound motor. So in compound motor we have two types again, cumulative compound motor and differential. So we will discuss cumulative first, cumulative compound motor. So how will this motor be? You have an armature, there is going to be a series winding and a shunt winding like this. Okay. So this is called as long shunt. That means the shunt is in parallel to both the series winding and the armature. What will happen in short shunt? In short shunt, you are going to have the shunt winding in parallel to the armature and series winding will be in series with the entire setup. Okay. So this is called as short shunt and this is called as long shunt. So the characteristics will be more or less same only for long shunt and short shunt. And the reason for this is, you will understand if you see the mathematical equations. Say the supply voltage is Vs for both the cases and let the back EMF be EB. Then what will be the equation for long shunt? EB is equal to the supply voltage minus drop across the series winding and drop across the armature, right? Now what is the current flowing through each of the series winding and armature? In long shunt it is same only, armature current, which is IA. IA into armature resistance RA plus series resistance you can take as RSE. Okay. Now what will happen in short shunt? Here EB is equal to Vs minus drop across the armature, which is IARA, and drop across the series winding. Now here the current is going to be not IA. This is IA, this current is field current IF and this is the supply current IS you can take. So this is going to be minus IS into RSE. But what happens is IS, here IS is equal to IA plus IF. But IF is going to be very negligible because the resistance of the shunt winding is going to be very high. So it will draw very little current, the shunt field winding. So you can approximate IS as equal to IA because IF is very small. Then what will happen to this equation? EB will simply become Vs minus IA into RA plus RSE. This is approximately you can write. So this equation and this equation are the same if you make this approximation. So that is why there will not be much difference in terms of the characteristics. Now what about the difference between cumulative and differential connection? See here in compound motor we have two fluxes. One that is produced by the series winding and other produced by the shunt winding. Now the flux that is produced by both these windings, if they are in the same direction with respect to each other, then it is called as cumulative. But if the direction of magnetic field is opposing, that means if one magnetic field is in this direction and other magnetic field is in this direction, then it is called a differential connection. If they are in the same direction, it is called cumulative. Okay. The first characteristic is the speed versus armature current. Now what was the expression that we got? EB is equal to Vs minus Ia into Ra plus RSE. Okay. Now EB you can write as K phi omega. Omega is the angular speed in radian per second. So this is going to be Vs minus Ia into Ra plus RSE. Now what is this flux phi here? This is the flux that is provided by both the series winding and the shunt winding. So you can write as phi Se, which means series winding, and phi Sh, which is the shunt winding flux. Now this shunt winding is anyways, it is independent of the armature current. But the series winding flux, this is dependent on the armature current. It is directly proportional. More the current that flows through the winding, more will be the flux that is produced. So now omega you can write in terms of the current as omega is equal to Vs minus Ia into Ra plus RSE divided by K into, in place of phi you will write Ka into Ia plus phi Sh. Here what we did, phi SE we wrote in terms of the armature current because it is directly proportional. Okay. So now this is the expression that we got. Now from here you can see what is the effect of varying armature current on the speed. Okay. See this omega and n, anyways they are different by only a constant. Omega is equal to 2 pi n by 60. Okay. So now if you see the armature current, if let us say if armature current is increasing, then what will happen to the numerator? It will decrease. What will happen to the denominator? It will increase. So what is going to happen? In this case, numerator will reduce and denominator will increase. So both of them have the same effect. When numerator is increasing and when numerator is decreasing and denominator is increasing, what will happen to the entire function? It is going to effectively reduce. So omega is going to drop. So the effect of increasing current is a drop in the speed. So the characteristics, they are going to be something like this. This is the speed n or omega you can take, and this is the armature current. As the current increases, the speed is going to fall. Okay, so this is the characteristic of N versus IA for a cumulative compound motor. Next, what are the torque versus current characteristics? T versus IA. So we know the expression for torque. This is given by K into phi into IA. It depends on both the flux and the armature current. So you can keep this as K dash to differentiate from the back EMF constant. Okay. So now once again, phi you can write as the series winding flux plus the shunt winding flux into IA. So here you are going to get K dash into phi SE, you can write as KA into IA. IA if you take inside, you are going to get KA IA square plus phi SH into IA. Okay. So compared to the shunt motor as well as the series motor, the torque is rising at a faster rate with respect to the armature current, right? Because for a shunt motor, T was proportional to IA, and for a series motor, it was proportional to IA square. But here both the terms are present. Okay. So the characteristic, if you are going to draw, this is the torque axis and this is the IA axis. It is going to rise like this. Okay. And finally, the speed versus torque characteristics. So we write omega in terms of IA, and IA we will express in terms of torque. Then you are going to get the relationship between N and T. But you don't have to do it because it will become very complex. The equations that we have here are pretty complex. You can do it as an exercise, but the graph is going to look similar to N versus IA. Okay, N and T. Why? Because T is proportional to IA. Even if not linearly proportional, it is proportional to IA. Okay. So speed versus torque will be similar to speed versus armature current. Okay. So this is going to be something like this. Next we will discuss the differential connection. So the differential connection motor is, in practicality, it is not used. Why that is the case? Because here the flux phi will be equal to phi SH minus the series field flux. And the series field flux, as we know, it is proportional to the current, right? So we can write as phi SH minus KAIA. Now if load increases, load increasing means IA is increasing, it is drawing more current. Then what will happen to flux? This is going to reduce. Now what is the effect of reducing flux on the speed? We know that omega is equal to Vt minus Ia into Ra plus Rse divided by K phi, right? So if phi is reducing, then speed will increase. So you can write here as flux decreases, the speed will increase. Now what does it mean that the speed is increasing? That means it is taking more load. So the current is once again increasing. So you can see that there will be a kind of a positive feedback. So there will be a runaway condition that will be produced here. As load increases, the speed will keep increasing because of the positive feedback and it will reach dangerously high value. So you can write speed of motor increases uncontrollably because of the positive feedback. So the differential motor is not used in reality. Okay, but if you draw the characteristics, then how are they going to look like? The speed versus torque or the armature current, if you take, it is going to just keep increasing like this. As current increases, that is the load increases, the speed will keep rising.